have to jump to probably point to any plot. So if anything doesn't make sense, just let me know. I also slept at 4 last night preparing for this talk. So if it doesn't make sense, likely my fault also. It's just the jet lag and everything. And we had wonderful dinner last night thanks to a few people here. Anyway, thank you for the organizers to make this happen. It's wonderful to be in Paris. And I'm going to talk about something kind of provocative, and having a spelling mistake, you can see learning science becomes leaning science, nothing to do with leaning forward or backward. With machine learning, steps to opening the Pandora box. I was told that I should not use Pandora box because it means trouble. I did not know that until recently, and I just imagine it's something, interesting. Regardless, I just moved recently from Berkeley and CMU to Flatiron Institute and Princeton University. For those who don't know about Flatiron Institute, who haven't been there recently, it's a new institute funded 100% by Simons Foundation, and just decided to treat scientists like we are working in Google or something like that. So we got really well treated, and basically I'm on permanent sabbatical. That's how I describe my life these days, which is pretty good. All the work are done with the students and postdocs. I probably don't understand half the plots if they didn't tell me what they are. So if all the faults are mine and all the good things are theirs, okay? Sia Hay was a student of mine, is still a student of mine from CMU, who followed me to Berkeley, down to Flatiron. Ying Li and Yufeng are postdocs at BCCP who works with us. Wei Chan's from Facebook, SciMac, and Barbara's also machine learning people from CMU, and SciMac was at CMU before, I suppose, or now as a faculty at UBC. And then we have other work that I also present a little bit that are contributed by the other people who are, some of them are actually in the audience. So talk to them, and hopefully I won't bore you too much because I'm standing between you and coffee. All right, here it goes. So traditional cosmology analysis, I know this crowd doesn't need reminding, but basically we take distribution of matter in the universe, pipe it into some summary statistics. Here is changing neutrino masses. Actually gives you different correlation functions in monopole and quadrupole. The top is monopole, the bottom is quadrupole, as a function of scale. And then you produce some constraints on important parameters like some neutrino masses in the posterior. So in this crowd, I think most of us know what is going on here. And so I said, okay, we can do better by combining summary statistics, all the summary statistics you can imagine. And then I said to myself, where do you go from here? And I heard excellent talks from Ben actually about how he looks at this. And I think I kind of stole some ideas what he thinks is happening. One is to investigate all kinds of cosmological probes, right? Clusters, AP tests, all these distance probes are different for these filaments that you probably all heard about. And then the other talk that I think Tom is going to talk right after this is to investigate what probes or create the probes that are going to contain most information. So I'm going to defer to his talk, not mine. And then there's the full forward modeling that a lot of people are actually doing. Urosha's group and Ben's group also have been doing, they're both doing a lot of these. With very, very intense computations, which are rapidly improving, and they're probably going to do really well very soon. How about something else? So can we use machine learning to learn and extract more information from the following data sets? That's what I'm trying to do these days. This is from 2016, back when I was at CMU, and I talked to my friends in machine learning and said, can we do a little bit different stuff than what people have been doing? And they said, well, why don't you try this? Here are the boxes of dark matter simulations with different cosmological parameters. We picked 3 of them, omega matter, sigma 8, and AS. And by eye, they look basically the same, but they don't. And here's the distributions of the simulations we generated for that particular experiment. It's published in International Conference for Alpha Machine Learning 2016. You can look it up. And so we used, back then, pretty good neural net, but now people are like, this is, have so much other cool stuff that you can do. But deep convolution neural net back then was, what we decided to do is 3D convolution. And the inputs are these little cubes of cosmological simulations. We actually chopped the boxes into smaller cubes to handle easier on this, basically this network. And we produce and predict cosmological parameters at the end. And what you're trying to do, I would say in words, is that convolution neural net basically performs nonlinear convolution on input volumes of the pixels and output the volume of scores, possibly of different dimensions, in this case, the cosmological parameters, and try to learn the underlying mapping between the two, the inputs and the outputs. And these nonlinear convolutions are basically trained with gradient descent. You can choose your best optimizer you like. So the output scores are consistent with the training sample. So let me just say it again, because this is kind of hard to take in right in no time. I know you guys, some of you guys do a lot of these, some of you don't. So let me just bring everyone in the same spot. So training says input n-body simulations with known cosmological parameters to train the convolution neural net. The validation set is to take the next set of simulations, and then you basically have the known cosmological parameters, and then you tune your neural net. And test set is that you put in n-body simulations that you don't know the cosmological parameters, and you predict it, okay? So that's what we did. That's sort of punchline of that paper back then. Here, the crosses, the blue crosses, what I used to do a lot, I still do a lot actually, which you use, actually not the blue crosses, the power spectrum, the red dots is what I used to do a lot, where you compute the power spectrum, you compare it to the theory to a certain scale that you believe, and then the ground truth is on the x-axis, the prediction on the y-axis. You can see that the crosses do a lot better, which is what the convolution neural net was doing. It's still biased, but later on we actually went back and realized that you can actually remove all these biases fairly easily by actually doing a little bit better on the neural net. So that actually can all be cleaned up. But the point is, it's a lot tighter than the red. And we thought, okay, this is weird. There are also other work by Sultan Hyman and his students, 2017, that looked at the weak lensing, and Francois mentioned that work too. And Francois has been doing this with weak lensing data set also. So I'm not the only one, but I think we might be the first one who looked into predicting the cosmological parameters from the data set stored directly. Data set in this case, very simple, idealistic simulation, so not the perfect situation yet. So now as scientists, I got into a lot of trouble showing this plot, right? Can we get, do we have errors? So we actually did have a different paper that you can look up. It's an ICLEAR International Conference for Learning Representations 2018. We talk about errors all over there. And can we interpret the model learn in the model machine learning here? So that's what I'm going to talk about today. And hopefully it won't bore you too much. What is the model learning? Where is the extra information coming from? Or more provocatively, can machine learning interpolate and generalize from the data set just like humans and find new physical laws? So that's extra provocative because it's before coffee. People are falling asleep very quickly, yes. I know, most people are just like, I need coffee. Okay, so can we interpret what the model is learning? So just remind you the plots, there's lots of spread on the red and not so much spread on the crosses. And we think the difference between the traditional method and what the machine learning is just doing is coming from the difference between what we can model analytically and the full information. So we made the following experiment, which is geared to learn from analytical modeling to the full information in the density field. So here's a movie, if you can see it. That's the white particles of the 2LPT, so analytical physics that you can actually just run through the simulations. This is running in not real time, but you can see that how the blue particles, which is the n-body that requires computing simulations, actually just cluster a little bit more. So the difference between the white and the blue is basically just this tiny small scale fluctuations in like the local scale, and very, very small scales where it clumps a little bit more. So that's what we're trying to learn. We want to give the white, can we get the blue? Actually make it even a little harder. We actually took salvage approximation and simulations pairs. So the training sets are pairs of simulation boxes. On the upper, that I cannot point to salvage approximation. On the lower corner is the numerical simulations that we ran. We have 8,000 pairs of them. Just for the audience here, we're actually running fast PM. I think these are 10-step fast PM simulations. They're not 100% unbody, but they're actually pretty close. You can look at Yufang's work and actually Urusha's group. If you can, any complaints about fast PM, you can blame it on me, but really it's Urusha's fault. It's okay. So the n-body simulations, the goal is that you input analytical approximation, which is salvage approximation, which takes seconds to generate, and output n-body-ish simulations, in this case, fast PM. By the way, we do now have access, thanks to Paco, who generated 10,000 n-body simulations. So we can rerun the whole thing with pure n-body. But I don't think it's going to make a huge difference. So some results here to show you. We're predicting the full phase space distributions of the particles, okay? We're not predicting power spectrum or whatever. We're predicting the actual positions and velocities of the particles. Truth is on top upper left-hand corner, truth on numerical simulations. In the middle is the comparisons between 2LPT, which is analytical approximation, and the residuals. Well, I mean, you're not surprised. They are different, right, from the 2LPT, from the numerical simulations, but not hugely different. And here's the machine learning predictions and the residuals. These are for the density field, by the way. And you'll see actually similarly the same plot for velocity. So I'm not going to bore you with basically the same looking plot. And then we check the following. We take the average of the power spectrum of 1,000 simulations. These are the test sets. And find the ratios of the true power spectrum. I just realized there's the screen over there. Over to the truth, which is basically a transfer function underneath here. So you can barely see on the top right-hand corner where this power spectrum or the prediction of machine learning is, because it's this orange line that's completely hidden under the green line. So the green line is the truth. You want to be as close as possible to the truth. As very smart plotting way that you cannot see the orange, which means we're doing pretty well. I mean, you say, okay, it's log scale, so let's put it not in log scale. So you divide it by the truth. That's the transfer function in the middle panel. And you can see that the orange line, which is basically hugging the 1, which is what you want to be, very, very well. The blue line, as you can expect, it will, not do so well in smaller scale at larger k, which is where the analytical approximation scheme fails. And here in the bottom is basically showing the error power spectrum, so lower the better. And the orange line has a very low error power spectrum. And 1,000 simulations were generated in 80 seconds, post-training and validation. So more validations on these predictions. We checked two-point function seems to be working quite well. The model is predicting quite well. Then you asked, well, two-point function is easy. If we have information that's non-Gaussian, this is the stuff that you want to actually learn. You want to at least test more than two-point function. So I went to three-point function. Thanks to the code actually generated by Yufeng, Nick Han, and company in Embody Kit, it implemented the three-point function fast computation by Slepian and Daniel Eisenstein. And so we can run this on 1,000 simulations very quickly. And on the left-hand side is the truth. It's the projected multiple three-point function. The monopole is probably, I think, normalized not exactly correctly, but we're checking it right now. But I think the shapes are all basically the same. The diagonal terms are actually blocked out now because if you see the diagonal, everything else is not going to show up very well. So we don't show the diagonal. But the rest is something you can take a look. Okay, sorry. The upper left-hand corner is the truth of the three-point function of various different monopole at different multipoles. So monopole L equals to 1, 2, 3, 4, 5, 6, 7, 8, and the two sides of the triangles, R1, R2 of the two triangles. An analytical approximation, if you run it on the 2LPT field, that's what you can get. And the bottom is the residuals. And here we get the machine learning predictions on the right-hand side. And you can see the residuals are dramatically better. And this is not exactly what we expected from start, because the subgroup approximation, which is the input, has fairly good two-point function, but not really three-point function. So getting three-point function working, we're actually very happy about it. So now we, as scientists, we have more questions, even more. So it seems like model's working quite well and quite fast. 80 seconds for 1,000 simulations fast, in my opinion. Why does it work? We don't know, not yet. Can we get core estimate of the error? So refer to that paper. So can we interpret the model learned in machine learning? So that's what we're going to try to do that next and try to understand where the extra information is coming from and maybe can interpolate and generalize. Let's see. So here we go. So how to interrogate this deep learning model? So here it speaks to, I think, a wider audience who doesn't do logical structure. We do simple analytical cases that are not in a training set explicitly and see whether these cases agree with the physics we already know as we know it. So check things that make sense, that we know what it is. B, we try to locate invariances in the system. This is actually inspired by multiple papers back in the days where people look at spring boxer system, a bunch of images, and they actually derived Hamiltonians and Lagrangians from it by the convolution neural net without actually going into any equations. So we said we must be able to find some invariances too. And then next, we try to look at where the information is coming from. So this is something we're still trying to work on. I'll show you some new results. Other suggestions are very, very welcome. And more provocatively, I'll show you, the generalization later on. So simple analytical cases. The first thing is very simple. For this audience, I'm not going to explain what Fourier modes are, but basically we input Fourier modes of one mode, of one particular k, as input. Instead of boxes like this, we literally just send in a plane wave. So you inject power at one scale as input, and here's the output. It's a very messy plot. You can blame this on me, but I secretly blame it to my students. Power spectrum on the y-axis, scale on the x-axis, transfer function in the bottom panel. And then you can see that the input is actually just the red triangle, one mode input. The UNet is the prediction network. By the way, for those who do machine learning, UNet is a variant of residual neural net, and Francois already told you what's residual neural net, so I'm not going to go into that. I forgot to tell you this a little bit more. And the fast PM is basically the truth, which is the crosses that are green. So if you have one mode entering, this is a nice to test intro cosmology courses. We have one mode going in, what do you expect coming out after evolution? So you do expect just one mode at exactly the same amplitude, which is what you see. You can see that the prediction and the truth and the inputs are all basically lining up there. That's the one mode in both different k. The left-hand side is different k mode from the right-hand side. K at 0.25 on this one, k of 0.15 on the left-hand side. And you can see that that's what you expected, and there's a bunch of noise. So the network's also learning the noise in the fast PM simulations. You can see how the orange stars kind of tracking some kind of noise off the crosses that you can see, the green crosses, which are the truth here. So it learns whatever crap you send it, okay? And then we try different things. How about if we change the phase of the input mode? So same k, different phases. As you expected, if you input different phases, the power spectrum actually in the end, the predicted power spectrum after this evolution or the networks being applied is the same. So that's good, which is what you expect from the theory. So it's checking out. Then we send in two modes. So this is the first time I show this plot. I'm kind of nervous about this. It shows the Fourier amplitude of the curl-free displacement field. So we want to look at the displacement field for many reasons. And then initial plane wave is the little diamond over there. Simulation is the crosses that blue. The Lagrangian theory is the second order Lagrangian theory, which is orange, and deep learning is green. So it's kind of complex. We look at the mode coupling of two plane waves. They're perpendicular to each other with the same amplitude, and the wave number marked by the gray diamond. It's chosen in a linear region where the perturbation theory is still valid, so we can check it. So what do we see? First, the plane waves stay at the initial amplitude, which is what you expect, the first point over there. It's just where it's supposed to be. And generated by the interactions, you do expect the two modes to interact. So you can see that new modes arise to the right of the initial mode, which is at smaller amplitude. And you can see that they do interact, and it's actually the simulation, the deep learning, and the LTL-PT all agree with each other. So that's kind of cool because that kind of proves that the interaction is actually happening as we expected. And then we also looked at what happened if you vary the amplitude of initial modes. You remember the two modes are perpendicular to each other, and we vary the amplitude of those two, and compare to the new one, and look at the interaction. So how much of this, I cannot point to it, but basically how much is the second one compared to the first one? So that ratio. And these display quadratic dependence, which agrees between theory, simulation, which is the truth, and the deep learning predictions. So I think that's actually pretty cool. And finally, we see a lot of extra stuff to the right-hand side of the second mode, which is past interaction term. And that's the stuff that we do not predict in second-order Lagrangian perturbation theory. I think at least some of it is the artifact of the simulation, which we feed the network as truth. The funny thing, and the, I guess cool thing, is that it is learning all the artifacts, if they're artifacts. If they're not artifacts, what are these? Maybe there's something we can learn about it. So this is still work in progress, but I'm happy to hear from everyone. Okay, so locating invariances in a system. So for those who don't work in machine learning, Mallah et al., well, not at all, actually, Mallah 2016 suggested that, if you want to understand deep neural net, it might be interesting to look at invariances and local symmetry, or even global symmetry of the system that you're learning. So we decided that, well, should at least look at the invariances that we think we understand in our system. So On the left-hand side is the input. We have the residual neural net in the middle, and we have predictions on the right. And what we're going to try to locate invariances, we try to just test the first thing we know, the rotational invariance. That's not surprising. We inject power at different k, x, ky, kz. They are basically the same amplitude, but different orientations, basically, in the end. And you can predict the power using the machine learning, and you can say that they basically agree with each other. Agree in the sense that no matter what direction you send it in, it gives the same power. And we do not explicitly tell the system that we actually have rotational symmetry. It just learned it. So we think it's pretty cool. So rotational invariance is learned. And the next question that I kind of want to pose to this crowd is like, what other symmetries and invariances do exist in larger structure? And I think it will be interesting to look from that angle and say, can we understand neural net from this particular direction? Next thing is, can we try to locate where the information is coming from? So we did something that people actually have looked into in fission a long time ago. Not a long time, okay, 2013. That's a long time in machine learning. That's like forever ago. So they look at something very simple. It's called saliency map. It basically plots the derivative of the output with respect to the input. If the signal, I is the input, if the signal is S, it's approximately some kind of transformation of the input plus some kind of constant shift, then you basically are looking at, if you take a derivative of it, that's to plot the saliency map. They call saliency, it's just really a derivative. So if you take an image on top, the saliency map will actually tell you, what are the interesting spots that you're actually changing. And here are the examples from fission. And you can see that there's not that much information, but you can see where approximately the information is coming from, just by staring at these. And so we try to do the same thing for us. So input on the left-hand column, output in the middle column, which is the machine learning output. And then where the arrow's pointing at is that I want the saliency map for this particular position, right? So for the first row, it's at the corner right there, where the output has nothing. So where does that information come from that is interesting, right, for this particular position? And it turns out to be coming from 4 corners. So for those who work in larger structural simulations, they'll be like, okay, yeah, because there's boundary conditions. So it actually makes sense. And we're like, okay. Middle column, we kind of point at the filaments. So in between the big clumps. And you can see it's very local. It's more or less right around where it is, which is what you think I think we make sense after we think about it a little bit more. Because what this learn model is doing is that it's sort of compressing locally. But this is our interpretations. I cannot prove it to you. This is just what the saliency map is showing us so far. And in the cluster, it's fairly like around the area also in the final row. So finally, more provocatively, can machine learning interpolate and generalize significantly from data, like humans, and find new physical laws? So this is extremely provocative. I think I'm going to just try to do the generalization part. We'll see. So we want to go outside comfort zone. And in this case, it's a training data distribution. So actually kind of responds to Salatin's earlier talk, where everything we feed the system is the training set. So can we sort of go outside of it? And so interpolation within a training set, can you extrapolate? That's what people like to describe. So we have CA maps of different cosmology. These are independent from the training set, completely independent. So the AS is going from the original A naught, whatever the AS value was, to 20% of it to 1.8, so 180% of it. And we ask ourselves, can we take this input, pass it through this neural net that has learned something from the Planck plus BAO cosmology from 2016, but doesn't matter, they're not changing that much. Can the learn model extrapolate and predict simulations, 60 phase-space distributions, and do not have the same cosmological parameters as the training set? So it has to predict the correct one, even though it does not have the training set. Okay, so we did that. So the experiment, just to remind us, we have trained, analytical approximation field combined with, pairs of Anglais simulations, in this case, fast PM simulations of one cosmological parameter set. We predict these particle position outputs using machine learning. It works well. now we're taking that away in terms of test set and replacing the test sets with different cosmological parameter sets. We're plotting a power spectrum with density view. You've actually seen this plot before, but this time we're plotting it with more lines. Solid line is a simulation of the truth. Long dashed line is prediction with ML. Short dashed line is 2LPT approximation. You can still run it with 2LPT, right? And now we're changing AS. And you've seen this before where the middle column is a transfer function. The lower column is the error power spectrum. So here it is. If you look at the power spectrum upper left-hand corner on top, you can see that the solid line basically lies on top of the dashed line, pretty long dashed line pretty much all the time. The dotted, well, the short dashed line or the dotted line is the 2LPT. You can see it's not doing super well, but it's, okay at large scales. And if you look at T of K, which is the transfer function, we can see that the long dashed line is really, really hugging 1. It doesn't hug as well as when you're in exactly the same cosmological parameters, but they're pretty darn close. So it's kind of intriguing. And the error power spectrum plot, of course, here, as you can see that the long dashed lines perform very well. And the only exception here is when this short dashed line actually do really well when you have AS equals to 20% of the original AS training set. So that's the only time that 2LPT was doing better. But in larger scale, you expect 2LPT to do really well, especially in such a very linear universe at that point. So then we also check the 3-point function, of course. The truth, you've seen this plot before, so I'm not going to go through all of them. Analytical approximation 2LP, residuals underneath it, and the deep learning prediction and the residuals. And it's really hard to see the residuals in the machine learning one. And actually, because it's AS equals to 0.2a, you actually see that there's not much 3-point function, which is what you expect. It's quite, nearly linear viewed. And similar situation happens when you have AS equal to 1.8 AS, the original AS. And you'll see that the residual is much, much simpler and much less in a deep learning prediction also. So now it's less possible because there are a lot of cosmologists who are really smart here. And I'm curious, what are your interpretations? I'm happy to buy beer or coffee to whoever offer a more interesting explanation than we've come up with. We've come up with lots of explanations. And we're trying to test them. Okay, people are too rich here. Nobody takes coffee or beer? Ben has some suggestions. So we haven't done what you suggested, which is just to do the point-to-point remapping. There's an old paper that Ben has written. Who's the first author? Right there. Exactly. And I saw it in the back. Sorry. And they looked at the point-to-point remapping. It seems like they do really, really well. So I haven't tested this yet, but it'll be interesting to try and take a look at what you guys have done again. Any other suggestions? Because Ben has told me this before, so you might not get beer. But I will buy you a cocktail tonight. Are you paying for it? Any other suggestions? Yes, please.
Try to change the parameters completely or add some other component to the cosmological model. See which type of differences you can obtain in your map.
That's a project of Elena Josama, who's working on it right now. So she's taking input, which is n-body simulations of traditional cosmological sets, which is the 6 parameters, and adding neutrinos. She wants to predict the ones with neutrinos, which is completely not even related, right? At some level, you ask yourself where that information is coming from. So you should talk to her about what she's found. She's just sitting. You want to wave your hand? Yeah, right there. What's that? So we didn't. So we're not doing that, but we are doing training from Illustris, dark matter to Illustris. So for those who don't know what Illustris, what the heck that is, it's hydrodynamic simulations. Supposedly they call them the best right now. So depending on which country you're in, they think they're best. And they have generated really nice galaxy simulations. And right now we have a bunch of students working on just going from dark matter simulations only to galaxies directly. And we'll see how it goes. I don't know how far they've done yet. But that's a great suggestion, yes. So this is exactly what Paco and a bunch of students and I are working on. So we are training from a very complex 21 centimeter simulations, which has supposing all the physics. And according to some 21 centimeter people, this is the best small box simulations you can ever have for 21 centimeter. And trying to make really big box of them. And the next goal is to say if we can learn from that mapping to also just map from dark matter directly to 21 centimeter. So we haven't gone that far yet, but we started this September, so. So you're saying that you want to have not different cosmological parameters as inputs, but different, say, this is a 21 centimeter map of different cosmological parameters. Mm-hmm.
And then use that system that you train to get information out of that 21 centimeter.
I have to think a lot more about this. I haven't done this before, but that's cool. But we do want to work on 21 centimeter for fun. Yep. I have to waste so much money for beer, but it's okay. Yes. So that was our original motivation a long time ago, to try to basically learn the whole evolution of the universe without using much physics, but just machine learning. And then I think I slowly come to realize why not use all the physics I already know, which is why we put in a stellar visual approximation as an input. And I think it's actually much easier to train to learn the residuals, which is the stuff we don't know, from the physics principle that we know to the full output of whatever, hundreds of steps of Anglais simulations being run. So that's what we decided to do. We actually did try and semi-failed, I guess, because the student decided to leave the field. I don't know. Maybe we scared him away. No, he's an undergrad at UBC that we actually had done a bunch of work that looked at the steps predictions and whether you can predict from one step to another without telling it any physics. And it turns out to be much harder than this problem. So we haven't finished that part yet, but that's a great idea. That was inspired by both Ben's work way back, like I think 3-5 years ago. When you do like forward modeling, then they actually change the initial conditions and see what you can predict in galaxy distributions and compare it to data. And Urusha's group's also doing quite a lot of that recently too. All right. Yes, there's someone waving the hand. Yeah.
Have you been able to try and, if you go and push as far as you can in any direction, cosmological parameters say,
so
see where it's
where it breaks, basically. Yeah, we're trying to do that. We haven't got to the point that's breaking 100%. But say the 0.2A, the 20% AS, you can see that it's not doing as well as the 2LPT, right? So at this point, then you should just use 2LPT at some point. But then on the other hand, we try to push, I'll show you the next example. We change omega matter. So the reason we try omega matter is because for AS, you can imagine just having island universes where you kind of intrinsically have some training set of universes of different AS, even within the same universe. So that's why we move to the next thing, which is a different cosmological parameter that cannot be 100% explained away by this island universe, suggestion. And we try to test omega matter equals to 0.001. And that one, the simulations have issues to produce. Not the deep learning, actually. We cannot produce a simulation. the simulation is not designed to do something like that, to actually generate. So we haven't done that, but we did do omega matters to 0.1 and a bunch of other numbers. So let me just show you the results. So 0.1, 0.3, and 0.5. And you can see that again, this long dashed line is doing significantly better than the short dashed one, which is not surprising, but it's how tight it hugs basically 1 at the transfer function that I'm surprised about. And you can see that the error power spectrum is also doing really well. But again, I think there are some boundaries at which like 0.1 omega matter is starting to hit quite close to, 12PT starting to do better at large scales, which is what you expect, but still doing better than 12PT at the smaller scales. So maybe 0.001, I don't know.
This is, and I think this would be the interesting thing to look at is why does it start feeling like, you can do 12PT and you can do better than aspirated, but testing that the bit where it does actually fail is also really interesting about finding it's probably mostly informative about what kind of architecture your network is not, like if that's not optimal for pulling out the information in the way that you want to. I think that's probably what's mostly informative about. But then you can learn because your architecture also informs you about the physical interpretation of the data.
So secretly, we're doing some other things. So I don't have plots for those because they're not ready. But basically, we realized that what the network is doing is doing something similar called Berger's equation. It came from like the turbulence people, which is basically when two particles came together, it stuck. They get them stuck together, which is kind of similar what we're trying to do between this white and blue particles. So we are trying to rerun the whole thing, but make a simulation that does the Berger's equation 100%. And we know the analytical solution of the Berger's equation. And then trying to look at the network, build as a simple network as possible, and try to look at all the coefficients and the correlations between the network. So we don't have results for that yet. And I don't understand them enough to tell you anything about them yet. So that's one thing we're doing. The second thing we're doing is that we're doing very, very simple small number body interactions to see whether we can predict the rules there first. So these are the directions we're trying to break the system, basically. So that's really great to hear all the suggestions, though. Okay, and here's the 3-point function. Again, when omega matters to 0.5, you can see the residual is still pretty decent with the machine learning on the lower right-hand corner. So what the heck happened? We didn't need to overlap the training set with the data set. We did not explicitly use transfer learning or meta learning, which is entirely two different fields that people are trying to say, can I transfer the knowledge I learned from one domain to another, which is kind of related to this, but we did not specifically use it. So it's doing some extrapolation without us telling it to. Maybe there's overlapping information somewhere between data sets. That's when I mentioned the island universes scenario. With omega matter, that island universe scenario does not explain it. As you can tell, omega matter changes the growth. So that's not captured in this island universes explanation. Or maybe the universe is fairly simple. Maybe generalization, extrapolation by the network is easy, quote unquote. I cannot prove this statement. There are many people who works in this field in machine learning that's looking at how to compress the model into simpler models. And I'm looking at it as, can I compress the simple physical rules or laws? So that's somewhere you can get into if you look at like Jeff Hinton's paper from 2010 or the recent paper in Malay et al. That I'm actually just mentioning. Maybe I'll finally get famous. So that's my possible climb of fame. The picture here, the person on top of me is my husband. The person below is Alice Hanaud, who recently climbed the face of El Capitan in Yosemite without ropes, 0 ropes. And so when I climbed with them and I was taking pictures, I said, oh, this is the way I become really famous because, if Pascal climbs really well, then, maybe we'll do something. But maybe it's understanding machine learning instead of climbing with Alice Hanaud, or compressing the learned model into physical laws, or discover new laws of nature. So I'll leave it at here. Thank you. So I'm really happy to try a lot of it just practicality, right? Because there's a really fast 3-point function code in n-body kit.
3-point functions are automatically learned by all.
Yeah, I do not have the power to test 4-point function yet because it would take forever to run the code I would write. But this one is fast.
That may be why our brains don't.
Yep.
If tomorrow you use your learned network on a new set of data, and you see a deviation, how much you can, how can you be sure or give a sort of uncertainty that it is a new physics which we are seeing in this new data set, or no, it can.
This is an extremely good question, right? So right now our training sets are not perfect, first of all. So before I would even input any real data in it, I need to make sure the training set is as close to reality as possible. And I don't think we're anywhere close that. You know, right now the simulations are not full embodied. Simulations do not have whatever I will observe the sky with, you know, with all the systematics and all the changing between galaxies. There's a lot of the work that has gone into the forward modeling community. Actually, there's a lot of them are here. And I think that machinery can be applied here, and there's a lot of that's actually happening. So I think, I'm not sure the talk, I don't think the talk covered it, for example, how do you put in galaxies, how do you put in survey selection function, how do you fake that there's a sky, all that stuff is extremely large amount of work. So we do not claim that we get to that point yet. We're at like baby steps right now.
Last question, then you choose between the three of you. You just went at the same time.
I can talk to you later.
No, like I said, I mean, one way to try to explain the generalization could be that whatever the map is that corrects to LPT to go to full n-body may just not really depend on cosmology. So, you know, it could be a sharpening operation mostly. I mean, that visually that seems to be what's going on.
So we tested it actually, and it turned out that so you can actually plot correlation function plots between the two different simulations with different cosmological parameters and with the same cosmological parameter. It's complex, but my point is that we were testing the correlation coefficient between learn model subtracted, well, prediction subtracted CA displacement, take that correlation with the input subtracted the CA, basically. Well, actually the input truth subtracted the CA. Take those correlations and with different cosmological parameters, and you see how they talk to each other. And then we realized that it wasn't 100% that situation. This is the first thing we actually tried. But I can explain with more plots later. This is a very, very good question because we were sure that was the case for a very long time.
I think this is kind of what I meant when I was asking you before about how do you break
Last one, then we go, okay?
So I guess maybe I missed exactly. What do you train using the you train the displacement, right? So, or is it the divergence of the displacement or the full displacement?
So we train actually with the displacement field, like the full
Okay.
displacement factor field.
So I guess a lot of that seems to be compressed into the divergence of the displacement field, and then there's some other stuff. Maybe it would, well, it might be useful to train the divergence plus some elements of the curl or something to get something that's relatively easy to plot, or I don't know. I can talk about that later. But.
That's a very interesting thought. We haven't tried that. So you're saying that we can train it with only part of the information instead of full displacement field. You're training only parts of the information.
Yeah, because like that's what 12PT and Zeldovich deal with, the divergence. So yeah.
Great. there's more questions, but I think there's coffee. I'll
it's-
let
we're
you decide.
we're getting late for coffee, so I suggest you discuss during the coffee break outside. Thank you. Let's thank the speaker.